We have finally waited for this day, the day when we rewrite the way of exploring the universe. Since 2015, astronomers have been observing gravitational waves formed by the collision of black holes. However, gravitational waves do not only appear when black holes collide. The gravitational waves produced by some very large and some very small black holes are also different. So, shouldn't other gravitational waves be discovered sooner or later? As early as 2004, astronomers collect data. On June 29, 2023, astronomers held a press conference to announce their 15 years of data. We can boldly say that there are gravitational waves traveling at the background of the universe, and these are very long gravitational waves propagate in space-time. Therefore, in the future, we can use them to explore the secrets hidden in space-time. What is a wave? What is a gravitational wave, and what does background mean? Normally, when we see waves at the beach, there are types of wave. One wave comes after another, and the distance between the waves is called wavelength. But when many different waves are added together, you can no longer distinguish which wave is which. In nature, many things exist in the form of waves. Sound is also a wave. If you want to find birds in a tree and they are blocked from your sight, you can still hear them. The birds' calls vibrate the air around them, and these air vibrations propagate as waves. When these waves reach our eardrums, they also vibrate our eardrums. Gravitational waves are also the same. When gravitational waves pass through our bodies also undergo changes. Similarly, in some unseen places in the universe, gravitational waves can propagate towards us. What is gravitation, or universal gravitation? Gravitation is a phenomenon that causes all things to attract each other, like how the Earth orbits the Sun or an apple falls to the ground. While Einstein told us that our universe is made of space and time, called space-time. If I give you a box now and you put different things inside, the more things you put in, the higher the density inside becomes. In the space-time we live in, objects with higher densities cause a stronger curvature in space-time. And black holes are objects that can pack nearly infinite amounts of matter into a single box. There are many analogs that compare space-time to a piece of fabric, which becomes curved or warped when there is matter present, also known as the curvature of space-time. For example, when two black holes collide, they will strongly disturb space-time, and this distortion of space-time propagates as waves in the form of gravitational waves. We can also view space-time as a grid of boxes and lines that surround objects, and the curvature of space-time is reflected in the bending of these grid lines. All objects in the universe move along these grid lines, and they would travel in straight lines if space-time were not curved. But if the grid lines become deformed, objects will follow the deformed lines as they move. When a gravitational wave passes through us, the grid lines of space-time will change, causing us to also change slightly, stretching us and compressing us. Hello everyone, nice to meet you for the first time. Soon I will conduct a small activity to simulate how gravitational waves affect the Earth in space-time. The props we will be using can be easily found at home. We will need a transparent container. The more transparent, the better. The second item is called gelatin powder. Later we will mix water with the gelatin to represent space-time. If you don't have gelatin, you can use jelly powder instead, but make sure it is a light color and not a dark one. The third item is for representing the Earth, and we will use marshmallow. First, pour hot water into the container, then add about 2 or 3 teaspoons of gelatin. Stir it. Our aim is to let it solidify. Once it has cooled down, place it in the fridge. Finally, add a marshmallow, which should float on top and might melt slightly. The upcoming process will be quick, so we should use a camera to record it and replay it later. After a few hours, we take it out of the fridge. Then we get a small ball or something similar. We are now ready to drop the ball into the mixture. When the ball dropped, space-time was disturbed. Gravitational waves propagate through it and affect the marshmallow. Of course, this is just a simulation and the actual situation is not as exaggerated. When gravitational waves generated by the collision of black holes pass through us, our size only changes by 1 part in 1 followed by 21 zeros. It is extremely small and cannot be detected at all. Therefore, scientists have built very long L-shaped gravitational wave observatories, such as the 2 4-kilometer long arms of LIGO in the United States. However, even at this length, gravitational waves only shrink by an amount equivalent to 1,000th of a photon within an atomic nucleus when they pass through. Luckily, our instruments can now measure such tiny changes. Gravitational waves come in different wavelengths, some of which can be extremely long, exceeding 1 light year. We cannot build instruments on Earth that are light years long to measure them. Clever astronomers thought of using celestial bodies instead of Earth-based facilities. They used the most stable signal emitter in the sky, millisecond pulsars, to monitor the space-time distortion. They emit pulses very accurately in the sky, more accurately than any clock on Earth. It takes 24 hours for the Earth to rotate once, and figure skaters can rotate in the air 4 times. We observe hundreds of flashes per second from the millisecond pulsars, which means they rotate hundreds of times per second. What? They are monsters formed when certain stars die, and although they are monsters, they are very useful. Astronomers use them as timing tools. When gravitational waves pass through these pulsars, the distortion of spacetime changes the time when their signal reaches Earth. Astronomers spent more than 15 years observing 68 pulsars, starting from the United States and then Australia, Europe, India, China, and Africa all joined in the efforts using the radio telescopes. They all saw the pulsars' flashes change in the same way, which means we have found evidence that a giant gravitational wave was changing the spacetime at the background of the universe. What creates these long background gravitational waves? What secrets can they tell us about the universe? We will talk about that next time.